Sure. I'm from University of Southern California. Can you hear me in the back? Good. Okay, great. So today I'm going to talk about electron-phonon coupling from GW perturbation theory, which has been briefly touched in previous talks. Today I'm going to give you a more in-depth of introduction. As we have learned through this week already, I mean, electron-phonon coupling certainly is a central interaction in condensed matter physics, material physics, and a lot of other disciplines. So for example, in transistors, solar cells, they play critical roles relevant to many aspects. Electron-phonon coupling basically comes from electrons interacting with lattice vibrations. For example, if you think of the green dots are atoms, they are in equilibrium positions. And once the atoms start vibrating, then that generates extra interaction, which we call electron-phonon coupling. Electron-phonon coupling can be relevant to many phenomena that I list here, but we've already seen a lot. So also from the lecture from this weekend, also by Professor Liu yesterday, we now understand that to describe materials properties using quantum mechanical approach, there are different electronic structure methods, and DFT is certainly one of the most popular and prevailing method, and GW is another very accurate many-body perturbation theory method. So GW method fundamentally is an excited state theory. So it gives a very good description of properties such as quasi-particle band gap, quasi-particle excitation energies, and so on. And on the other hand, DFT is a ground state theory where the Cauchy orbitals are fictitious orbitals. So in the real materials, the many-body interactions can be mapped into this very complex object called self-energy, where fundamentally speaking, it's non-local, where you see R and R prime, and it's frequency dependent. And within the GW method, it's approximated as G times W, hence the name GW method. If you, if I would like to remind you, G is a Green's function and W is the spring-Coulomb interaction. Within DFT, if we want to describe if we want to use DFT to describe quasi-particle properties, then the view of that is that the self-energy is the exchange correlation potential in DFT is mimicking the effect of the self-energy sigma, whereas in DFT, this quantity is local and static. And we have seen this a similar figure yesterday, that if we use the GW approach to calculate, for example, the band gap of semiconductors, it agrees pretty nicely with the experimentally measured values for very wide range of materials. Whereas if you use DFT with standard approximation, such as local density approximations, the band gaps are systematically underestimated. So it is a natural question to ask, are there self-energy or many-body effects in the electron-phonon coupling? So the remaining of this talk, we're going to go through this and break down and to see how we can answer and tackle this question. If we want to try to understand if there are self-energy or GW self-energy effects in material, a straightforward approach is to use frozen phonon technique, as also introduced by Marius in the first lecture of today. We can do that because, as introduced by Feliciano on Monday, if I write down a eigenfunction, which let's say Cauchy equation, the wave functions, the potentials, they are all explicitly dependent on all the atomic positions, Ri. And if we change the positions to a new position by adding a small perturbation, say, away from equilibrium, then we can get a new potential. And we can, of course, use finite difference approach to compute the differences between the potentials and calculate the rate of the change, basically the derivative as an approximation. There are many advantages of it. And one of the advantages is that it can be combined with any electronic structure methods. For example, standard LDA, GGA approximations, or advanced hybrid functional, or as Professor Mazzari introduced on Monday, Koopman's functional, or GW or DMFT or other approaches. basically because you just need to change your structure, and then you compute a new quantities, then you look for the difference. So how do we do that? So this has also been mentioned by Feliciano in his lecture, that naively we can just move the atom and see what are the changes in the electronic structure. Then we can try to extract electron-phonon coupling information. So this is an example of diamond where if we want to see an impact, or we want to see the electron coupling to an zone center phonon, then that's relatively straightforward. We just work within a primitive unit cell and just displace the atoms following the phonon eigenmodes. Then we see a change in the band structure. So the blue lines are the band structure at equilibrium position, and the red lines are the ones with the inclusion of phonon perturbations. And you'll see that this doubly degenerate band splits, and there are also changes in the band energies at other cases. And in fact, for the zone center phonons, if the shift is small, the change of the band energy directly corresponds to electron-phonon matrix elements for the intraband transitions. But phonons, as we know, that a gamma-centered phonon is definitely not enough in most cases. So what about finite momentum phonons? How can we extract the information, let's say, within frozen phonon technique? So basically, for finite momentum phonon, if you have an initial state and you have a phonon that carries a crystal momentum of Q, that can possibly scatter this state from 1 to 2, where 1 and 2 electronic states, they carry different crystal momentum, where the difference is Q. And to simulate that effect, we can again use frozen phonon approach, or we can try to understand the behavior using a frozen phonon kind of a concept. So let's say, for example, if we have a phonon mode introduced in a supercell with displacement, basically we introduce the change of the potential, delta V, on top of the original Hamiltonian at the equilibrium position H0. So we now have a new perturbed Hamiltonian. So if we just look at the subspace made by 1 and 2, these two states, we can just compute the matrix elements of the subspace of the Hamiltonian, and this is what we get, right? This is the diagonal matrix element, which is just the original energy of state 1 and 2, and on the off-diagonal matrix, on the off-diagonals, we have the scattering strength. And that's a very simple 2x2 matrix that can be diagonalized by hand, and this is the energy, new energy that we get. So basically, this equation tells us that, well, the energies will be different, as we can imagine. But I want to talk a little bit more of this simple model, because it gives us some deep insights. So there is a special case. The special case is suppose 1 and 2 are degenerate in energy, which means basically they are of the same energy. So in that case, this expression will be reduced to a simpler expression. For example, this term is 0. In the case of the degenerate case, we will have the new energy plus minus equals the E1, epsilon 1, which is their original energy, plus minus the potential change. And if you recall what the potential change is, it's induced by the atom displacements of a finite Q phonon. And basically, it's just the G times the displacement that you moved. What it really means is that if the two states are degenerate, that means when you build a supercell, the bands will be folded at the zone boundary, where now you have a degenerate two states. And you apply atomic displacements, they will split. And the splitting is proportional to the band gap opening at the zone boundary. And actually, this is a pretty good technique that you can extract electron-phonon interaction of finite Q with any electronic structure code. So people have done that. Okay, so here, before I talk about the literature, let's look at an actual example still with diamond of finite momentum Q calculation. So this is the band structure of diamond, and this is the same gamma L direction that we see in the previous slides. And again, these bands are doubly degenerate. So if we introduce a phonon Q equals L, where L is 1/2 0 0 with respect to reciprocal lattices. Then that effectively, if you want to simulate the phonon, then we will do a 2x1x1 supercell. And that basically fold the band right here at the middle between gamma and L. So we fold the band, and here at the zone boundary, originally it's doubly degenerate. So at exactly this point, now we have 4 states degenerate. Then we apply the phonon perturbation, and the 4 states will split. So by looking at how much displacement you applied, which you know, and by looking at how much the band energy splits, we can extract the information of G, which is a pretty powerful approach. And you can see that electron-phonon coupling is tightly connected to the electronic structure and energies in the material. And people have done that a lot in the literature, actually, try to study if there are self-energy effects or how much self-energy effect there are in certain materials. So one example is this superconductor potassium-doped barium bismuth oxide. It has a TC experimentally measured value of over 30 Kelvin. So over 10 years ago, people have done frozen phonon calculations, and what they did is exactly the process that I just described. So for example, so this is a particular calculation at with a phonon mode at the R point in the brane zone. That's 1/2, 1/2, 1/2. So basically, you can build a 2x2x2 supercell, and then displace your atoms, and then see how the band gap opens at the zone boundary, and to extract the G's. So in this work, people did that for this BKBO material and realized that the electron-phonon coupling constant lambda from LDA is around 0.3. But if you do a calculation with hybrid functional HSE, lambda is increased by a factor of 3. That leads to a huge jump of TC from 0.6 to 30 Kelvin, roughly, and that agrees nicely with experiment. So here we see that certainly we can use the electron-phonon coupling, use the frozen phonon approach to extract the electron-phonon coupling. But there are certain conditions, right? For example, this material is a relatively isotropic material, so you can more or less use one point to represent the whole brane zone, although in most of the cases, it doesn't sound like a good idea. And also, you need to have some states near the Fermi energy and so on, so that it can represent the superconducting states. Well, this is one example. Another example is also done 10 years ago, where also includes Samuel, who did the work. So in this work, the authors calculated the band gap renormalization from electron-phonon interaction, which is covered also in the lectures earlier. So this electron-phonon coupling can give you 0-point renormalization of the band gap at zero temperature, as well as temperature dependence in the band gap at finite temperatures. So if you look at the value from DFPT and with GW correction using frozen phonon, there's a big difference. And the one with GW correction is actually pretty nicely captured to agree with the experiment. So this is through a different way of extracting information, but basically the information is there. If you want to build a supercell, you can extract the correlation effects using any electronic methods that you would like to use. So then basically, in this whole week, most of our practices are based on linear response. So what are the differences? So frozen phonon approach, as I explained, is you explicitly build a supercell, move the atoms following the phonon wave vector Q and phonon eigenvector patterns. Then you extract the difference and compute the finite difference slopes and so on. It's very easy to implement. In the most basic sense, for if you want to see, for example, band splitting, you can also extract both harmonic and unharmonic effects. For example, as what Zacharias showed for thermal configuration sampling. So it is a very powerful approach. And for linear response, it's tackling the problem from a different perspective. Basically, you need to rewrite your equation in a perturbative way, and also assume all the changes are to the linear order, then you can actually factor out a phase factor to represent the wavelengths of the phonons. Then the remaining part becomes a periodic, lattice periodic quantity. Then you can solve for that. Then you can pretty much solve everything within a unit cell. And the advantages is that it's computationally much cheaper. That's one of the advantages, because for each phonon mode, the computational cost is the same, and it's also similar to a unit cell, like a standard calculation, band structure calculation. Whereas frozen phonon calculation, the computational costs increase significantly because most of the electronic structure methods are not linear order methods. And one of the most successful linear response approach is DFPT, which has been a central topic of the school. So the idea is if we can build a linear response approach like DFPT at the GW level to describe quantities that we want, especially to get the electron-phonon matrix elements, which can be very efficiently and directly evaluated within linear response. And let me just quickly remind you what electron-phonon matrix element is. It represents a scattering amplitude of an incoming state hitting a phonon and scatter to another state. Or we can look at this diagram that you can have an initial state hitting a phonon and scatter to a different state. So the amplitude is very straightforward. It's a sandwich between two wave functions and by the scattering potential, which is the change of the potential induced by phonon. So a few years ago, together with Professor Li, we developed this GW perturbation theory to basically compute electron-phonon coupling within this linear response formulation and within the GW approximation. So the key ingredient here is that we need to construct and calculate the linear response or the derivative of d sigma dr, where sigma is the GW self-energy and r is the atom position of all atoms within a unit cell. So now we are able to calculate the GW matrix elements, electron-phonon matrix elements for all the ones that we need. And the relation between the GW matrix elements and the DFT matrix elements is that the contribution from the exchange correlation potential is being replaced by the contribution from the man electron self-energy, which the replacement is pretty similar to how we construct the GW band energy as well. And with this method, now we can systematically, efficiently, and accurately calculate electron-phonon coupling going beyond DFT. So a little bit more about what is actually being done, still on a rough picture scale. So what we need to do in GW perturbation theory calculation is that we need to construct a few quantities. And we work with Abinet, which takes a lattice vector convention instead of a Cartesian coordinates, but it's just a simple basis transformation. Anyway, so the main quantity we need from DFPT is the first order change in the wave function, dq psi, which can be constructed within first order perturbation theory. It is slightly different than what DFPT Stern-Heimann equation directly generates, because if you recall, some part or most of the time, the valence manifold has been projected out. And to run GWPT, we need to recover to the full form of the first order change of the wave function. And there's some gauge consistency implied in this expression that also becomes a requirement in the calculation, that you cannot mix and match different wave function at different steps. You have to stick with one set of wave functions, because the first order change of the wave function, the first order change of the wave function inherits the gauge or the arbitrary phase of the zero order wave function. So with the first order change in the wave function, we can construct the first order change of the Green's function, which takes a form that d psi psi plus psi d psi. And with delta G, we can now construct the change of the GW self-energy operator, delta sigma, which is a energy convolution between delta G and W. And once we have this operator, we can evaluate their matrix elements between any states of interest. So here, if you are a little more careful, you may notice that we have dropped a term, because if sigma equals I times GW, then D sigma should be DG times W plus G times DW. And indeed, we have taken a constant screening approximation where we assume the change in the screening dielectric environment induced by phonon perturbations is relatively small. And it's a pretty good approximation and has been verified early on even before GWPT by using frozen phonon approaches. And I'd also like to point out that it's equivalent to a well-justified approximation of dW over dG equal to 0 that has been set in the GW beta substitute equation calculation. So then let's see what we can do with GWPT. So let me also bring back again this diagram. The self-energy can include many terms, for example, electron, electron-phonon, and so on. And they can they can come into each other in complicated ways. For example, in the most simplistic case, we can have the GW gamma electron self-energy. We can include or don't include phonon effects. And also for the electron-phonon self-energies, which they live on a different energy scale than the electron self-energy, we have van Migdal and the Biwaller self-energies as well. So if we take this van Migdal self-energy as an example, there are few things we can update, or say there are few places we can include the self-energy effects into the electron-phonon self-energy. So for example, for the propagator G, instead of using DFT eigenvalues, we can use the GW eigenvalues. So that brings a G to have the self-energy effects. And for the electron-phonon vertex or electron-phonon matrix elements, we can also now use the GW level matrix elements, which sometimes can give a big qualitative difference than the ones from DFT. So both places can play important roles in certain materials and in certain phenomena. And for gamma, for now, we drop it in most practical calculations as 1. Another quantity is this D, is the phonon propagator. So within the current workflow, the phonon propagators are still taking the phonon frequencies from DFPT. So you may wonder if we need to correct that or not. But I would like to point out that if you think of the phonon frequencies coming from DFPT, it's based on ground state total energy in the adiabatic limit. And DFT is a ground state theory, and the total energy is generally pretty good compared to quasi-particle properties. So given that background, so most of the time we still keep the D as the ones from DFPT. And mostly correct or include the self-energy effects in the ones associated with the electrons. And this is a practical workflow that to run GWPT. It's actually quite involved. We interface with Abinet, EPW, and Vanier 90. And there are several places that if one were to run the calculation, that there are several places need to be very careful. Well, first of all, the rough idea is that we start with a DFT calculation, then we can do DFPT calculation. Then we can feed these input to Berkeley GW and run GW calculation and GWPT calculation. And with that, we can do some symmetry unfolding, which means that we save computational effort by reduce the Q grid. Then we use some wrapper code to prepare files for EPW to read, interpolate, and calculate practical electron-phonon properties or quantities of interest. And also, to use the Vannier interpolation, we need to connect, well, this has been already connected, but we need to use the Vannier rotation matrices and feed it directly to EPW. So there are several places need to be very careful, especially the gauge issue, because the electron-phonon matrix segment itself is a gauge-dependent quantity. So you cannot just, it's wrong to mess it up. So in order to keep consistent of the gauge throughout the whole workflow, so the green boxes highlighted the quantities that they should be stay within the same gauge. So that involves the Vannier interpolations. So basically, the gauge consistency is needed to construct the zero and first order self-energy operators, as well as the matrix elements, and also because of the Vannierization process. Okay, so with the workflow established, we can now do calculations and see what we can get. So this figure Professor Li has shown yesterday, and basically we have taken GWPT to validate a set of materials where in a lot of the simple metal cases, the GWPT, DFPT both agree reasonably well with the experiments. However, in one material that I've already mentioned that people known a decade ago, that in this material, PKBO, DFPT will significantly underestimate the electron-phonon coupling magnitude, whereas using hybrid or advanced functional or many-body approaches, it gives a much better agreement. And we can use this BKBO as a demonstration to see what GWPT can achieve. So this material, as I mentioned, it has an experimental TC around 30 Kelvin at its optimal doping when X or the whole is 40% doped into this material. And this is a band structure. And you see it's a pretty, in terms of electronic structure, it's pretty simple and friendly for us. Just one band, smooth and simple Fermi surface. And as I mentioned, one can use frozen phonon to extract the information, right? So here we first do the same thing and to verify against GWPT. So here, basically following the previous work, this is the point they choose. If you make a 2x2x2 supercell, then your supercell Broughton zone along this direction will be folded at this dashed line. And then we have this dashed bands when the band structure, when the crystal structure is not perturbed. And now, if we include atom perturbations, they start to split, right? And as I mentioned also earlier, the splitting is proportional to G times delta X, your displacement. So we can do explicit calculation to see that. So these thoughts are explicit frozen phonon calculations. And if you look at, for example, the blue points, they are based on DFT. And if you displace the atom by different magnitude, the splitting becomes bigger and bigger. And similar, you can do that with GW band structure calculation too. Very straightforward. Those are the red crosses. And now we have a few lines. These lines are not fitting. These lines are directly calculated by DFPT and GWPT respectively. So we know the matrix elements. Then we multiply the displacement. Then we get the lines. So these are actually direct linear response calculation. And you see that within small displacements, they agree almost perfectly as they should be. So this also again shows that, okay, we can certainly extract electron-phonon information using supercells if you want. But this is a special case, right? This is a special case that this Fermi surface relevant state happened to be able to capture it within 2x2x2 supercell. In general, it may not be. So that's why we developed GWPT. And with GWPT, now you'll see we can access the whole Broughton zone information of interest. So this is a distribution of electron-phonon matrix element G, the magnitude of G calculated using DFPT and GWPT for a particular phonon Q for a particular KZ slice. And we are looking at the distribution of KX and KY. And you see we can access all the bromine zone information, and each dot represents a calculation of a single unit cell. So in this plot, we're basically sampling the phonon and electron bromine zones by density of A by A by A. And if one were to calculate this information using frozen phonon, then one need to build an A by A supercell, which correspond to over 2,500 atoms with frozen phonon, and you need to do a GW calculation on that. So that sounds really bad. But now with GWPT, we can easily access this information. And we can also look at the physics, what we can get. We see a strong renormalization. You see the color is much bigger. So that means self-energy effect certainly in this material enhances the coupling strength. If we put those into numbers, we can quickly estimate the TC. First, we can calculate lambda. That's also been done through the week. And in our calculation, we find a DFPT value about 0.47, whereas GWPT is about 1.14. Experimentally, it has been measured. So this is a measured spectrum where you can see there's a gap opening near the Fermi energy. And this gap size is uniform when you go through different parts of the bromine zone. So that represents that it's very likely an S-wave superconductor, which typically is an indication of electron-phonon coupling driven superconductor. And with lambda, we can plug it into Macmillan-Allen-Dynes formula, which roughly has an exponential behavior in lambda for TC. And this is our calculated TC for a given mu star, 0.16. And you see that the electron-phonon, the superconducting TC estimated with GWPT agrees nicely, not only in magnitude, but also in the doping trend. In this material, whereas DFPT is significantly underestimated, as we already know. So this shows that for this material, BKBO, it actually is a strong electron-phonon coupled superconductor where correlation effects has a critical role to enhance the coupling strength. And I would like to give another example on superconductivity, which shows that not only the matrix elements are important, but the self-energy in the band structure also can be quite important in certain materials. So this is another material that was discovered as a superconductor a few years ago, infinite layer nickelates or strontium-doped neodymium nickel oxide. So people have been looking for superconductivity in nickelates because they sort of take it as analogs of unconventional cuprate superconductors because of a similar electronic structure. Nevertheless, after the discovery, DFT calculation has been done and found that the TC is less than 1 Kelvin. So this is structure of the material, which we call it in the 112 phase. And it's the infinite layer structure is here. It's grown on top of a substrate. And here is experimentally measured phase diagram, and this red curve shows a superconducting dome where the highest TC is around 20 Kelvin. But again, DFT TC is very low. So we did calculation on this material, full GW calculation, which means that the band structures are calculated using GW methods, and the electron-phonon matrix elements are calculated using GWPT method. And we see a drastic change in the electronic band structure. And basically, there are two bands relevant to the Fermi energy in this material. And the blue ones are the ones of 3D transition metal. And there's orange and green bands that is relevant to neodymium, the rare earth orbital, and a interstitial orbital or IO orbital we label in this work. So basically, you see from from DFT to GW, this orange-green band has been put down such that the presence of this neodymium and interstitial orbital characters has been significantly enhanced through GW self-energy effect or through other self-energy effects. In fact, if you do hyperfunctional or scan functional calculation, you also see similar trends. So that means, for example, if we look at the dense states, at the DFT level, there's very minimum this orange component, which is from neodymium and IO orbitals. And within GW, the captures the presence of the orange components got significantly enhanced. That pretty much changed the whole electron-phonon coupling landscape of this material. If we calculate the standard Ellashberg function of a square F using fully DFT ingredients or fully GW ingredients, we see a huge difference. And at pretty much all frequencies, we see that the electron-phonon coupling is enhanced. And the overall integrated lambda, electron-phonon coupling constant lambda, is enhanced by a factor of 5.5. And furthermore, we can, of course, break down because we know where all the interactions are from. So we can break down and figure out where are they, which part contribute by how much. So there are two major effects. First, the self-energy effects in the band structure enhances the coupling constant by a factor of 3.7. And second, the self-energy effects in electron-phonon matrix elements, which one can get from GWPT, enhances the lambda by a factor of 1.5. So you multiply them together, that's over a factor of 5 enhancement. And that also completely changed the electron-phonon, the phonon-mediated superconductivity possibility in this material. So this is a calculated, we use full GW ingredients to solve Ellashberg equations in EPW. And this is the density of the distribution of the gap, superconducting gap in this material. And we see clearly a bimodal distribution, whereas the blue part is projected to nickel band states, whereas the red part is projected to neodymium and interstitial orbital components. And we see that this component, whose presence has been enhanced in GW calculations, shows a very strong electron-phonon coupling and hosts a strong gap, strong gaps on the Fermi surface. And that makes the superconducting TC around optimal doping or at lower doping to be around 20 Kelvin in good agreement with experiment. And also the doping dependence also follows the experimental trend. This calculation shows that basically we can make a prediction in our based on our calculation that the self-energy effects can possibly let the phonon-mediated superconductivity show up. So one cannot quickly exclude this possibility in this material. And okay, so as also discussed through the week, there are other signatures that can be studied in electron-phonon coupling, and one of them is very important, the spectroscopy signatures that one can review using, for example, angle resolved photoemission or APLIS. There is a very interesting phenomenon called photoemission kink in different materials. One of the most famous one is photoemission kink in cuprates. This has been introduced also. So you see instead of a straight band, which is a non-interacting band, you see the bands have two segments pretty much here. And that represents a coupling with the boson mode. So the nature of the boson mode, if we want to know them, we need to do accurate ab initio calculation to try to see if that explains the experiment. And the physics is kind of pretty straightforward, can be captured by the electron-phonon self-energy. If you consider a single phonon mode with constant frequency, that will give you a peak behavior in the real part of the electron-phonon self-energy. So if you add that self-energy to the original linear Bayer band, that looks like a kink. So that's pretty much explains this behavior with a general electron boson coupling. We can calculate the self-energy, and we can calculate it using both DFPT and GWPT. And for one of the cuprates, doped lanthanum copper oxide, we see a big enhancement in the real part of the self-energy from GWPT over DFPT. So that again shows that self-energy effect significantly enhance the electron-phonon coupling in this material. And if we put it back into the calculation to calculate the spectral function, then we clearly see a kink, and we can do some analysis and directly compare to experiment. So this is a dispersion. The circles are extracted by experiments, and the red line is a GWPT, and the blue line is a DFPT value. And we see good agreement, and not only in the kink, but also in line width, their temperature dependence, doping dependence, and so on. So this again highlights that this type of calculation, we do need a method like GWPT to be able to capture the full effect. And the kink is actually not only in cuprates, it's in many other materials. Here I quickly give another quick example, which is a Kagome superconductor. This material has intrigued a lot of interest because it holds a variety of phases. And here we we take a quick look at the photo emission spectral function. Its Fermi surface, as you can see, is quite complicated. So using frozen phonon, the similar frozen phonon technique to extract the information would become impossible in these cases. There are multiple band crosses the Fermi level, but if you focus on the alpha band and beta band, and experimentally, people have seen different kink behavior. In the alpha band, there's a major kink around 30 MeV, whereas in the beta band, there are double kink structure. So now we can do the full calculation, and this is a simulated spectral function. We actually clearly see that the alpha band has only a single kink and the beta band has two kinks. And if we plot against the dispersion relationship, that also agrees nicely with experiments. And again, because we're doing perturbative constructive calculation, we can break down things. And we can also understand the different behavior by projecting out or decompose the self-energy into different vibrations. And basically, we see different atoms, they contributed, the vibrations of different atoms, they contributed at different frequencies that give you this multimodal behavior in this Kagome superconductors. Okay, so I've talked a lot about the method and application, but I need to address how expensive GWPT is, which is, as you may imagine, truly very expensive. So this is an example of boron doped diamond, but we use virtual crystal approximation, so pretty much it still remains within a unit cell, 2-atom unit cell. If you do DFT calculation, the calculations are run on Frontera at Tech. If you do DFT calculation, including generate wave functions and so on, it's roughly to the order of 10 CPU core hour, which is very straightforward. If you use one node, that's just a few minutes. If you run DFPT calculation, which you have been running this week, you know that for every phonon mode, you need to solve a self-consistent equation. And the computational cost is about 2 orders of magnitude higher, which is expected because you have basically 3 times n atom times number of Q points of phonon modes to be included, to be calculated. If you do GW calculation, you also tried yesterday, it's more expensive than DFT. It's roughly to the same computational cost as if you run a DFT calculation. But then if you multiply it by this factor, here's a GWPT calculation. So for this 2-atom system, it costs over 50,000 CPU hours just for 2 atoms. And computational cost, you can think of it as about 100 or 1,000 times of the resources needed for GW calculation. So it is indeed very computationally heavy. But we have a solution. So the solution is to go to seek for high performance computing resources and capabilities. And in that case, the code need to be very efficiently developed and parallelized. So this is a work led by Mauro Delban, who has been here the whole week. And this is also covered by the lectures yesterday. And in our code, the Berkeley GW is very scalable to high performance, the fastest supercomputers. And thus, it enables us to do very large systems. So this was a calculation done 4 years ago. It's a GW calculation on a defective silicon. It contains over 2,700 atoms, and the calculation was run fully on Summit machine, which by then was the fastest supercomputer in the world. And the calculation has reached over 53% of the peak performance, which is truly efficient. And the whole calculation is finished in 10 minutes. So this really gives us the opportunity to scale up the calculations, not only for GW, but also for GWPT. So nowadays, this is one of the recent examples that we calculated. We are able to run GWPT calculation of a system of 63 atoms, potassium 3, carbon 60. This is a unit cell. Basically, it's a molecular crystal, which is also a superconductor. And we calculate the GW band structure as well as the GWPT matrix element to calculate the superconducting properties of this material. And this is enabled by running on now the fastest available superconductor frontier at Oak Ridge. And it is worth mentioning that this is also the current stage is that the Berkeley GW can interface with the latest version of EPW, which is done by Nick Pand and Andy, that they enabled the latest interface. And also the calculation is quite non-trivial that's carried out by my postdoc, Jingyang You. So this calculation actually is done with GWPT on supercomputer interfaced with the latest version of EPW, where we have used the full bandwidth Migdal-Eliashberg theory introduced by Professor Marjin earlier. And the reason why we need that is that this material is, you can see it's a narrow, pretty narrow electron band material where the phonon energy is about to the same, it's to the similar scale of the electron band width. Okay, so to sum up, I would like to mention that with years of development, we are now able to carry out many Electron-Phonon calculations with interoperable software packages, in particular here, Berkeley GW and EPW. And that allows us to have some advanced functionalities. Especially, we can calculate the electron properties, quasi-particle properties at the many-body level, as well as the electron-phonon coupling, including the self-energy effects using GWPT. And all these can be combined with the capability of the latest version of EPW, which give access to a lot of phenomena of interest. And all these calculations now can be carried out at the full many electron level. Okay, so lastly, but not the least, I would like to thank my collaborators and especially Professor Louis, Professor Dislip, Dr. Dislip and Dr. Delbin, who are at the school, and other collaborators over the years. And I would like to thank the opportunity for the school to making a lot of great things happening, as well as my research group. Also thank the funding agencies and computational resources. And before I finish, I would like to advertise the 10th Berkeley GW tutorial workshop and 5th Berkeley Excited States Conference that is happening just in 2 months. The location is in Oakland, California, close to Berkeley. And it's basically a 1-week event. The first 3 days is a similar workshop setup similar to the EPW school. Whereas the last 2 days, it's a conference. It's a full 2-day conference of roughly 20 invited talks by renowned researchers in the world talking about excited states phenomena. And the registration is open, and we would like to see you again in Oakland in person in 2 months. And here is a barcode you can scan and to learn more about the information. Thank you very much.
Thank you, Professor Li, for a very nice talk. We have time for questions.
Very nice talk. So you showed that there is a very good agreement for the electron-phonon coupling strength between the GFPT and the experiment for elemental superconductors. But you showed that, I mean, it's different for the oxides, right?
Yeah.
So can you comment on the implication of the GW perturbation theory for the superconductors which are other than the oxides?
Can you repeat the last part?
Implication of the GWPT theory for the superconductors which are other than the oxide superconductors.
The effect of GWPT for superconductor with and without oxygen, is that the question?
Yes, that's
okay.
So
the idea is not only oxygen, not only superconductivity. So basically, you can use GLPT to calculate other properties as well. I think you can also calculate transport property of oxides, which behave sometimes strange. So I think the question is more on why oxides has a stronger effect, right? So that is reasonable because oxides, the transition metal together with oxides or other d electrons with oxides tend to be more localized, and this is less captured by DFT simple functionals anyways. So that is a situation where, I mean, naively one can expect a stronger correlation effects showing up. Yeah, whereas in simple metals, everything's delocalized, fully screened. It's there's not much there. Yeah.
So how do you maintain the gauge consistency between the linearization and your SCF calculations you mentioned on?
The gauge?
Yeah.
So basically, one has to be very careful. So here, let's say if you run DFT calculation and you generate a wave function on the full K grid for all bands, you pretty much set your gauge. All the remaining calculation has to be based on the same wave function. You cannot say, for example, you generate the binarization rotation matrices with one wave function, and in GW you generate another set of wave function because, for example, you need many bands. You have to start with one wave function with many bands that fits the need for all steps. In that way, you keep the gauge consistent.
Right. So my question is regarding the frozen phonon method. So in that case, why do we use the finite difference formula instead of the symmetric difference formula? Isn't symmetric difference formula more accurate with similar complexity?
Why do we use frozen phonon? Because of what? Can you say that again?
In frozen phonon method, why do we use the finite difference formula instead of the symmetric difference formula? And the symmetric difference formula is the difference between plus r and plus delta r and minus delta r divided by 2 delta.
Well, yeah, I mean, you can use that, of course, no problem. I'm just using this equation to basically give the idea. Yes, you can use a symmetric, yeah, you can use r plus delta r minus delta r and divided by 2 delta r, no problem. Or you can keep going to higher orders. Basically, the idea is to just show that the quantities can be extracted using frozen phonon. And this is one way to extract G, and there are other ways to extract different properties. For example, you can extract the band gap renormalization using a different formula, or you can extract thermal properties in optics using a different formula like Zacharias presented earlier. So this is just a demonstration of the idea.
One more question in the semiconductor, superconducting properties, right?
Which one?
In I think it's slide 25.
I didn't have a label. What was it about?
So it was about TWS, the annual review.
Is it still on there? 25. Okay. Sorry.
So in this slide is the right hand side plot. Why is the why is the calculated plot is showing a slower decrease than the experimental plot?
Yeah. Well, yes, that's a very good question. So first of all, experimentally, there are a lot of uncertainty too. This material is known to be very not clean. There are many defects, so that affects. And also, theoretically, there are other effects, doping-dependent effects that we may not be able to capture. And here, we are capturing the doping-dependent band structure effects, but we are not capturing the doping-dependent electron-phonon matrix elements effect because it's too too computationally heavy. So we're assuming that the G's are not changing much, but that could also be the reason why.
Stand, Professor.
Yes.